recording. Yeah, sorry for forgetting the recording. Okay, however, this is luckily okay. This is just the introduction to the lecture. Okay, so the recording we start from here, but okay, also we still have to go into the main topics for the lecture. So just to recall and replace the things over the recording. Okay, we have a three-dimensional world, image formation process, build an image from a three-dimensional world, image processing, how to process the image, computer vision, how to go from the image to the representation, okay, into our computer. So how to build into our computer a representation of what is inside our image. So computer vision is understanding the content of image and videos. What instead is an image is a bidimensional representation of our three-dimensional world. So in some ways, a reduced representation of what is inside our three-dimensional world that gets stored in some way into our computers, mobile phones, and so on. Any question? Okay, sorry again for starting the recording a bit late. So first of all, okay, before looking into detail into the image formation process, a brief overview of what is an image. Okay, we are going to see more in detail this later in the course, but since okay is one of the key concepts, we just introduced basically the basic ideas about the image, okay, object, let's say, of the image thing. So what is an image? An image is basically a bidimensional function or signal, okay, that we denote with the usual notation f of x and y. That basically, okay, we've seen a represent, okay, a bidimensional representation of what has been captured, okay, by our camera. So ideally, it is a continuous bidimensional, okay, function or signal, f of x and y, where x and y are the spatial coordinates, so represent, okay, the location of a pixel of a point we are considering, and the value of f for each location represent the so-called, okay, intensity or gray level of the image, that is basically the amount of light that have reached that specific pixel, that specific point. This, of course, corresponds to the concept of a so-called, okay, grayscale image. So in this way, we capture the amount of light, but not the color of the light. Since nowadays, of course, all the images that we are working with will be color images, we need to introduce also the color image concept. In order to represent also the color, the key thing that we need is basically the wavelength, okay, of the light. So we'll see later in the color lecture, the color depends on the wavelength of the light. So what in some way sets the color is the wavelength of the light that is arriving. So the complete correct representation, okay, for a color image would be a three-dimensional function. Let's call it, okay, for example, fc of x, y, and lambda. So it's a function of three things, the x and y, the two spatial coordinates, and lambda, that is the wavelength. And this function gives us the intensity of the light for each specific wavelength. This allows to capture also the color. The problem is that also this representation is very big in terms of amount of data that we need, and also is very challenging to be acquired. It cannot be acquired with a standard camera, requires spectrometers, special devices. So what we commonly typically use is an approximation, okay, of a real color image that is basically made by using, okay, three bidimensional functions. So the key idea, instead of representing, okay, all the spectra of a light, we represent it basically, we represent, okay, the color of a light by using three components in a suitable color space. We'll see later what are color spaces. So for example, the very well-known, okay, RGB color space, we have three bidimensional functions, FR, FG, and FB, that represent the amount in some way of red, green, and blue light. This is, of course, an approximation of a complete spectra. It's not representing completely, okay, what is happening, but we'll see is enough, especially compared to what we can perceive, okay. We'll see this more in detail later in the color lecture. For the moment, okay, just get the idea, then we'll see better why we can approximate it with just three components and not 4, 2, or 7, for example, okay. Second important thing, okay, we have to remember, okay, ideally the image is a continuous bidimensional signal. The value of f can be any positive real number, but recall, okay, we are working with computers, we are working with mobile phones, with, let's say, electronic devices. So what we can store into our computers are not continuous signal. We need in some way to sample the signal, okay? So what we are going to work with in this course, okay, what we are going to work with, you want to use computers, mobile phones, digital cameras, basically everything nowadays, are digital images. What is a digital image? Is an image in which X and Y are discrete quantities. So basically, okay, the same signal f of X and Y is sampled over a regular grid. And the values of f are both discrete and finite. Okay, so you have okay, discrete values also for the function, and also they are typically inside a predefined range. Okay, so it's discrete values and also not all the possible numbers, just possible ranges of values from 0 to 200, from 0 to 1000. We see the typical representation is from 0 to 255 because it corresponds to 8 bits for each pixel. This is, let's say, the most basic standard representation. Of course, there is a trade-off between the amount of memory we need to store the image and the accuracy, okay, representing the image values. Any question? Okay, this is just a synthesis of what we were saying before. We are working with digital images. Okay, so X and Y, the spatial coordinates are discrete, and the value of a function are also discrete and also basically forced to be into a specific predefined range. So basically, if you look here on the slide, okay, let's say this one is the ideal, okay, image signal is what we should see. What we really store into our computer is this representation here, okay, in which the image is in some way quantized, okay, the spatial location are quantized, and also the image values are quantized. So notice that not only the shape, okay, is in some way quantized, but also the possible range of gray values is also quantized. This also corresponds to the fact that to store the image into our computers or our devices, what we are going to use is a bidimensional data structure that is basically a matrix. So notice, okay, this is from the OpenCV library we're going to use for the labs. Notice the object we use to store the image is the so-called mat object, where mat, of course, stays for matrix. Okay, so from the point of view, okay, of a computer library, let's say that holds our image, the image is a matrix, is a bidimensional matrix that contains all the values for all the pixels. In the case of grayscale image, we have a standard, okay, 2D matrix with grayscale values. If you use a color image, we will have basically 3 matrices, okay, or a, let's say, X by Y by 3 matrix that contains, okay, the 3 components, red, green, and blue, for example, in the RGB color space. So notice here, for example, okay, just to go into the practical things, okay, you see the call, okay, to create an image, for example, of 640 by 480 pixels. We create a matrix, okay, with a specified dimension that is basically, okay, the number of pixels in the 2 dimensions in our image. And here notice, okay, in the case of a grayscale image, we have a single component, okay, for each pixel. In the case of a color image, we have 3 components. So in the case of a color image, the size, okay, let's say is W by H by 3, for example. Okay. Of course, okay, now I place also some code snippets just to link to what we're going to do later in the labs. For the moment, of course, we still have to introduce the lab part, the OpenCV library, and so on. But I think in any case, it is interesting to see the code in some way that corresponds to the thing that we see in the lecture, so you can join, okay, the theory and the practical part. Any question? Okay, first very important thing, okay, how the image get built. What does we really capture, okay, with our cameras, our video cameras, and so, or our, let's say, imaging system, imaging sensors. Very important thing, okay, what we capture is the light, okay, that arrives to the camera, and the light basically depends on 2 things, okay. So what is going to happen in the real world is that typically, okay, first of all, to build an image, we need an illumination source, okay. So we have something that produces light. If you are outdoor, this can be the sun. If we are inside, it can be a lamp, a light bulb, and so on. Okay, so we have a light source, or device, okay, or the sun in the case of outdoor scene. There is something that produces the light. Okay. So the sun, for example, produces the light, the light produced by the sun travels, okay, into the space and reaches the object of which we are taking the picture. So imagine that our camera that is here, okay, this is our camera, is taking a picture of this object here. What happens is that the light reaches our object, gets reflected by the object, and reach our camera, okay? So notice the path of the light starts from the sun, for example, reach the object, bounce over the object, and enter into our camera. What is going to happen into our camera, we'll see in a moment. From a moment, okay, imagine that there is some lens, some hardware, some things that some way, okay, capture the light that reach the camera, and the light basically gets projected over, okay, the film in the very old cameras or the CCD or CMOS sensor into the recent digital cameras. Okay, so there is okay, basically a plane from a point of view of a geometrical structure on which we are able to capture the light that arrives. This can be the film in the very old times, or can be, okay, a CCD sensor or a CMOS sensor in recent electronic devices. The CCD sensor, okay, basically each pixel is able to capture the amount of light that have reached that specific pixel. And so basically the image gets created over our CCD or CMOS, and then, okay, it gets processed, okay, by the electronics into the camera, we get our matrix with the data. So what is an imaging system? Okay, a camera basically is a device that is able to collect the light reflected by the object and to build a bidimensional image from the light that has reached, okay, our camera. Very important thing, what we measure, okay, is not that the camera captures the object, okay? The object does not produce light. What we capture is basically the light of a source reflected by the object. So it's a combination of a light source with the reflection properties of the object. In other terms, okay, from a mathematical point of view, the value f of x and y, okay, that is the content of our image, is the product of two things, okay, the light from the illumination source and the reflection, okay, properties of the object. So notice what we measure, okay, is not directly the illumination source, is not the object in some way. What we measure is the light, okay, starting from a light source, so let's say I of x and y, multiplied by the reflection of the object, that we call, for example, R of x and y. By the way, to connect also to what we are going to see in the color lecture, when you see that an object is red, is green, is whatever, blue or so on, what really happens is that the light that is typically produced by the sun or by the lamps is, let's say, quite white. Then also the color of the light source can change, okay? So the color of, for example, of the light of the sun is different from the color of the light of a lamp and so on. So for example, the sun emits light in the whole spectra, in a very large region of the spectra. A red object is an object that basically absorbs all the green and blue, for example, light, and reflects only the red light, okay? So the reason because we see an object red, for example, is because it reflects the red light and instead stops all the light that has a color different from red. Same thing, okay, if it's green, yellow, or whatever you want. So what we measure is the product of the two things, okay? The light from the source and the reflection of the object. This is also the reason because we can see, okay, a different color for the same object if you illuminate with different light sources. Notice that what we would really want to capture, okay, what is needed also by our computer vision algorithm would be in some way the reflection of the object. So we want to get, okay, which is the color of the object, the properties of the object. But what we can measure is not directly, okay, the reflectance of the object is the product of illumination by reflectance. So if we, for example, if we change the illumination, we change also the color of the object that we see. The color not of the object, but the color that we capture, okay, with our camera. And this we see will be a problem for many computer vision algorithms because you want, for example, to recognize the same object in different images. But if we have taken the image, okay, with different lighting condition, the color would result different even if it is the same object. If you want to perform object recognition, this is a problem because what you measure depends also on illumination, but in some way you need to remove, or we'll see we need algorithms that are robust to illumination change. Any question? Okay, so key problem, okay, how to how do we see the world? How can we go, okay, from a 3D world to a bidimensional image? This is a problem that has been, okay, widely studied from very many years ago, okay. It's been a problem, okay, even from the ancient times. Of course, if you go back 1,000 years, there was no computers, no mobile phones. So the first people to look into these problems are the painters, okay, that tried in some way to build the images, okay, not using the camera or the computer, but by drawing them. If you look at the very old paintings, okay, from the 12th century, you can look that they do not look really very realistic. There is something wrong, okay, in the representation that you get over the image. You are not able to capture really the 3D structure of the world. The first painters, okay, to be able to start to properly handle these problems were a bit later, from let's say 1,300, 1,500, okay. For example, one of the very first painters to be able to capture, okay, what happens was Giotto. By the way, we are in Padova, okay, you know that Cappella degli Scrovegni here is one of the masterpieces of Giotto, is one of the most important artwork from him in the world, probably history of art. And one of the reasons for which this painter and this Cappella degli Scrovegni is a very important milestone, okay, in painting, because it was one of the first examples in which we can really see the 3D structure, okay, captured into the painting. Another painter, okay, also from this area that was very good in doing this was Mantegna, for example. And then, okay, if you go a bit later, okay, in the Renaissance, in the 15th centuries, for example, Raphael, you can start to see finally, okay, the proper, let's say, perspective, proper reconstruction, okay, of the 3D world into the paintings. So what does they understood? They understood basically how the perspective projection works. The perspective projection is the key process, okay, that maps the 3D world into our image. And this, by the way, the same principle that is used both, okay, by digital cameras and all these devices, and also by our eyes. It's also the same thing that happens inside our eye. Okay, so key problem, how do we see the world? How can we go from, okay, let's say our 3D world to, okay, the image that we get over the CMOS or over a film, okay? So imagine that we have an object and we want to take a picture of this object. So first, a basic idea, let's say that we want to try to design, okay, a camera, okay? We do not know the technology, we want to start from scratch and design a camera. Say a digital camera if you want to replace, okay, the film with a CCD in more modern times. What do you think will happen if we place a CCD or a film, okay, in front of an object? Do you think that is going to work? Any guess?
We need a lens.
Okay, the lens will be the next step, okay. We're going to go to look into the lens in the next lecture, okay, next week. For the moment, okay, it's true that we need a lens, but okay, now we try to do something simpler. Just start from this idea here. What is going to happen in this case? Focus, for example, on the red point, okay? Mm-hmm. The light, okay, starts from the sun, let's say, and reaches the red point, okay? What happens is that when the light reaches the red point, it gets basically spread out in many possible directions, okay? So the light that has reached the red point gets reflected by the object in many different directions, which is, okay, the so-called Lambertian, okay, surface model, that the light that reaches a point gets reflected in all the possible directions. So the light that reaches the red point, okay, get reflected, okay, to all the various pixels into our CCD or CMOS or all the various locations in our film. If you focus now on a different point, for example, this one, the light is also this point here, and same thing happens. So notice what is going to happen. For example, in this point, we have a mix of light from the red point and from the gray point. So each single pixel in our image is going to capture light from all the possible points of the object. We get a mixture of all the various parts of the objects, and we do not get a reasonable image. Okay? So this idea is not going to work. Any idea about not to solve the problem. Okay, simpler than the lens. Let's say the lens is a possibility, we see how it works. But it's very simpler idea to solve this problem.
We need a hole.
Yeah. Key idea, we can place basically a barrier with a small hole in front, okay, of our film or our CCD. Okay, so we place in front of a CCD a barrier that is basically, okay, let's say a plane with a small hole. By the way, okay, the drawing we have here is bidimensional because, okay, the PowerPoint slide is 2D. Of course, you have to imagine that the thing is in 3D. Okay, so it's not, okay, a line with a hole, is a plane with a small hole in the middle. Okay, so in the 3D, let's say, representation would be something like this. Okay, we have a plane and a small hole in the middle. Here is a profile view, let's say, of a thing. Okay, of course, for drawing reasons. So we place this plane with a small hole. What is going to happen now? Let's start from a red point. The light reaches the red point, gets reflected by the object. But notice what happens. Okay, all the various refractions get stopped, except for the one that passes through the hole. When we go to the gray point, same thing. Okay, all the light rays get stopped, apart of one, that is the one that passes through the hole. Okay. So first of all, this works. Yes, let's see the key thing. Okay, each point basically gets only the light from one location of the object. So on this point here, we get, okay, the top of the tree. Here we get the gray point. Same thing, okay, if you try to do for all the other points of the tree. By the way, this small opening is known as the aperture, okay? We see when you do the thing about practical digital cameras, why it's called aperture and how can we control this thing in a real digital camera. So it works, but there are a couple of problems. Do you see any problem?
The image is inverted.
Yeah, first problem, okay, the image is inverted. What we get here is, okay, something, okay, sorry for the bad drawing of a tree, okay. We get a reversed version of a tree. This is the first problem. The image is inverted. Of course, this is a very easy problem, okay. You can easily get that with just 2 lines of code, okay. You can basically flip the image and solve the problem. So this is a problem, but it's an easy problem. You can just add 2 lines of code into the hardware of your camera that reverse the Y dimension, and this is very easy to be solved. There is another problem instead that is a bit more challenging and more critical, okay. What do you think of the size of the hole?
The size of the hole will be, like, I think, comparable to the resolution of the image. So
yeah, this is the idea, but this is a bit of problem, okay, because this is the idea, okay, it should be in some way comparable to the resolution of the image. But the problem is that ideally, okay, to get this model perfectly working, you need an infinitely small hole, okay. The smaller is the hole, the closer you get to the ideal model. Notice if you have a large hole, you get back in the problem of before that multiple rays pass through the hole. So from one point of view, you would need a very, very, very small hole to have the theoretical model that perfectly works, to have a very good resolution, have no blurring and so on. On the other side, if the hole is too small, there is not enough light passing through the hole. So we do not have enough light, we are not able to capture, okay, even to measure how much light has arrived. And also there are diffraction effects if the hole is too small. So there is a critical trade-off on the size of the hole. You will see this is a very key problem in designing real cameras. However, okay, for the moment, okay, now we are in the, let's say, theoretical part. We assume that the hole is infinitely small, okay, it's very, very small. This introduces practical problems, and we see is quite critical for real-world cameras. And by the way, it's the reason for which we use also the lenses, as one of you was suggesting before. Okay, so given this, we can introduce, okay, the so-called pinhole camera model or perspective projection model, that is a mathematical model that captures, okay, these ideas. So let's design, okay, the first very basic camera. How is our camera made? There is, let's say, a box on which, okay, we have on one side, okay, the hole, and on the other side, okay, we have this plane here that is, okay, the sensor on which we are going to build the image. Here we have, okay, our real world. We have, for example, our object in the real world. So the camera captures all the light that passes through a point that is a very small hole that you can see. First of all, let's introduce, okay, some notation. The hole, okay, is called also center of projection, that is typically abbreviated with COP or just with the letter C. So the position, the hole, okay, is the center of projection, is the point C, and is basically the point from which we capture the real world, okay? So the point that in some way, okay, is the origin of our reference system, okay? The point from which we capture our picture is the center of projection, and this is basically the small hole in the pinhole model. This one we are going to denote with the letter C, okay? Or COP, one abbreviation. The plane on which we build the image, so basically the plane that corresponds to the CCD, CMOS, or film in the old cameras, is called, okay, the imaging plane. Sorry, this is the general projection. Second thing, okay, is the imaging plane that we denote with the letter R, that is the plane on which we are going to build the image. Very important parameter for the design of the camera is the distance between the central projection and the imaging plane. So the distance between the pinhole, okay, and the plane that represent, okay, the sensor is called basically focal distance and is denoted with the letter F. And we see is a very fundamental parameter in designing the camera. By the way, okay, to connect with what we are going to see for real cameras to what you have, okay, into your real digital cameras, the focal length is what basically controls, will see the zoom of a camera, okay? So to connect with the practical things, when you change the zoom, what you are really doing, you are changing the focal length, the focal distance, or focal length is also called. This, of course, on the, let's say, good cameras, okay? So if you have a reflex, a real digital camera, this is what is going to happen. With the mobile phones, instead, there is just some software interpolation. So this corresponds to when, okay, you change the zoom and something is really physically moving, okay? So this is what happens in the digital cameras, not what happens in mobile phones or webcams or similar devices. Next important thing, okay, is the so-called optical axis, that is the line that is perpendicular to the imaging plane and passes to the center of projection. So this blue line, okay, you see on the slide is the optical axis and is the line that passes through C and is perpendicular to the plane R. And the intersection of this line with the imaging plane, okay, is called the principal point. We denote with the letter P star. In some way, is the center, let's say, of our image, okay? So P star, okay, is the intersection of a principal point with the optical axis. Sorry, this is the intersection of the optical axis with the imaging plane. In the ideal model, okay, it stays exactly in the middle of the image, but be careful that in real cameras it's not exactly in the middle for practical reason related to the precision in building the cameras. Very final thing that we can introduce is the so-called focal plane, that is instead the plane parallel to R containing the center of projection. So in our box camera is the other side of the box, okay? The side of the box that contains the center of projection. Any question? Just a moment. Okay. So first of all, okay, we need to introduce also some, let's say, coordinates reference systems. We are going to use, okay, two different reference systems, okay? Because we have a three-dimensional world and we have our image. So the first coordinate system that we need is the one of the real world, so the one that sets, okay, the positions in the real world, that is, okay, the so-called 3D world coordinate system that we denote with X, Y, and Z, okay? This is basically measured in meters, centimeters, kilometers, whatever, okay? And are the coordinates, okay, of the objects into the real world. Well, instead, we are going to use the letters U and V to denote the bidimensional camera coordinate system, so the locations over our image. Notice that in this case, okay, the unit of measure instead are pixels, okay, so 3D world, X, Y, Z, positions in meters into the real world, bidimensional position into the image, U and V, position in pixel, okay, into the image. What we want to compute is a mapping between the two spaces, okay? So you have a point coordinates x, y, z in the 3D space, which is the corresponding pixel UMV on which the